Alright, so in this section we're going to take the ground reaction force that we talked about in the previous lecture and we're going to apply it to our bridge in the form of a single degree of freedom model. So you'll notice I'm in a new notebook now, so the first thing that I've had to do is, well, I've got my usual imports at the top, then I've redefined some of the constants that we defined in the last lecture. So if you're continuing on and coding everything in the same notebook, you obviously don't need to do this, but because I'm in a new notebook I do. So I've got the pacing frequency, dynamic load factor, time step, time vector, and then the vertical ground reaction force, which is made up of the static component and the dynamic component that we talked about. Then I've brought in my Duhamel integral function again, exact same function, copy and pasted from where we wrote it previously, and now we're ready to get going on the new stuff for this lecture. So as we kind of said already, the whole approach here is going to be to simulate the vibration response of the first mode of vibration of this bridge. And we know that that means that we can simulate the vibration response using a single degree of freedom system. Now, if we had a more complex structure with multiple modes of vibration, it'd be very easy to combine the modal responses in the usual modal superposition way. But we're not going to bother doing that. We're just going to simulate the response to the first mode of vibration. And then using the mode shape, we can map that single degree of freedom response back onto the different locations in the beam. And we'll see that as we move forward in a couple of lectures time as we build out a simulation or a visualization of the vibration response. Okay, so first things first here, we need to take that ground reaction force, that Fn, that was this, or Fv we called it, that was this guy here, and we need to turn it into a modal force Fn. Now we can do that very, very easily by multiplying the force by the mode shape value that corresponds to the pedestrian's location. Now this is changing as the person moves across the bridge, but because they're moving across the bridge at a constant velocity, we can get their location as a function of time very, very easily. So what I'm going to say here is that the location of the pedestrian is equal to whatever the pedestrian's velocity is times the time vector. And that gives us the pedestrian position as a function of time. That then allows us to construct phi as being equal to np dot sine of pi x over L. Okay, so we said that the mode shape was the sine of n pi x over L. Well, n is equal to 1 because this is the first mode, and x itself is now a function of time, which means that this value of phi that we're going to get is itself a function of time, which will then allow us to multiply that phi value by the force vector. All right, so what have we got? This is going to be math.pi times xp divided by L, the span of the bridge. All right, and then to obtain the modal load, so that's the equivalent load that we would apply to the single degree of freedom system that represents the first mode of vibration, it's just going to be Fv times phi. Okay, and that's your modal load. Okay, so we can execute this now, and we see Vp is not defined. Did I run this? I didn't define Vp, the velocity of the pedestrian. I did define Vp, there it is there, look, Vp, let's run this and let's try that again. Okay, excellent. Okay, so there we've defined the modal force. Now before we go ahead and apply that to our single degree of freedom system, let's just visualize it, let's just see what it looks like. So we'll define a figure and a set of axes and then we'll just plot that force against time. And we'll just say the label is modal load. And we'll bring in our usual housekeeping. Okay, so let's run that and see what we have. Okay, excellent. So what are we looking at here? If you visualize what's actually happening here, we've got a pedestrian that's starting off over here, all right, and they're moving across the bridge. So they're moving across the bridge, Now this is a time axis, right? So this is the time it takes them to move across the bridge. And you can see that as they're moving across the bridge, we can see their footfall force is being scaled by that mode shape value. Okay, remember the mode shape value was just a half sine wave. And what we're really taking from this is the dynamic influence of the pedestrian on the first mode of vibration is growing to a maximum where the mode shape is a maximum at the center of the bridge and it's diminishing thereafter. So this very clearly gives us a visual representation of the dynamic influence of that pedestrian on the first mode of vibration. So now it's just a matter of providing this force along with the time vector directly into our Duhamel integral for our single degree of freedom response. Now before we can do that, we just have to define some of our bridge parameters again. So we said the mass per unit length was 2000. We worked out previously that meant the modal mass was a half times the total mass. So that's going to be a half times m times the span of the bridge. we said that the damping for our bridge was 2.5%, so that should be 0.025. We said we were going to specify a modal frequency of 2.5 hertz, which gave us an angular modal frequency of 2 pi times 2.5. And then we had the damped angular natural frequency, which was omega n times the square root of 1 minus xi squared. Okay, great, so we can execute that, and now we have to find our parameters. Let's feed the force and time, or the time and force, into our Duhamel integral function. So we'll pass in the time vector and that modal force Fn. We'll assign the output to a variable called response, if I can spell, and execute that cell. So now we can plot our response, simple as that. So this time, plotting time versus, now I'm going to, just because I want it to look right, I'm going to plot the negative of the response because I want it to be a downwards, deflection, because obviously the forces are acting down, and we'll drop in the usual titles. Okay, excellent. So there is the response of our bridge as the person walks across it as a function of time. Okay, so what are you actually looking at here? You're looking at the response. Now remember, the horizontal axis here is time. It's not distance. It's not position along the bridge, right? So this is time. So what you're actually looking at is the vertical oscillation at the center of the bridge as the person moves across the bridge, right? So the vertical oscillation, again, at the center of the bridge, as a function of time, is shown here. So the vertical oscillation is going to be very, very small when t is equal to, well, when t is close to 0, because the person has just moved onto the bridge. And so as they're just stepping onto the bridge, the first few meters of the bridge, you know, we'd expect the oscillation at the midspan to be quite small. But as they start to get closer to the center of the bridge, the magnitude of those oscillations is getting bigger. But what we're also seeing is the static deflection is increasing. So you're looking at two things here. You're looking at a static deflection superimposed on a dynamic oscillation. So that's why I've called it the static and dynamic response to the bridge. And so it would be kind of interesting to separate out those two influences, separate out the static deflection of the bridge due to the self-weight of the pedestrian, and then the dynamic effect due to their dynamic component of their ground reaction force. That component that's at 2 hertz, the pacing frequency, or whatever we said it was, 1 point something hertz. So let's just do that. It's pretty straightforward to do. We've written all of the code. We've done the hard bit. So all we have to do now is call our functions. So I'm going to define Fn static here as just being equal to the static self-weight times phi. And I'll then define Fn dynamic as just the bit of the ground reaction force that's left over, and of course that gets multiplied by phi as well. All right, and now we can call our Duhamel function again. So I mean, you can really see if you're new to programming, you might be tempted to not bother, you know, encapsulating your code into a function. Obviously, if you've done plenty of programming in the past, you understand the merits of you know, using functions. But you can see it here. Like we're going to call this Duhamel integral Duhamel function many times, and so having it as a function rather than having to retype out the code every time is super handy. Right, so let's just call that response static, and we'll do the same thing, except we'll say that's dynamic, and obviously we need to pass in the dynamic load. Okay, so now we're going to calculate 2 different responses, and we can go and visualize those. So this time I'll just set up a couple of subplots, so slightly different syntax. So I'm going to define a figure, a set of axes, but I'm going to let those axes, I'm going to let those equal to plt dot subplots. Okay, I want to define a figure size as being equal to, let's just say 14 for the width and 10 for the height. And then we got to define the number of rows. We'll say there's going to be 2 rows, and then the number of columns, n calls is equal to 1. Okay, so what I want to do is I want to plot the 2 components separately. So the static deflection as a line, and the dynamic oscillation as an oscillating line in the top plot. So we can visualize the 2 separate components, and then I'll replot this below it, just so we've got a good comparison. Okay, so to access the first plot, we're going to index into axis 0, and we're going to say axis 0 plot, and what do we want to plot? We want to plot time versus the negative of the response. But we want the dynamic response, right? So that's going to be dynamic. And let's also give it a label. the label can be dynamic. Okay, so let's just see what we get. So we've got a bit of tidying up to do, but that's just the dynamic component of the response, okay? Now let's also visualize the static component, right? So onto the same set of axes, I'm going to plot the static deflection. And we'll just say static. And let's make it red. So I'll call it a red line. Okay, great. So there you have it. I mean, there's very, very clearly visualized the two separate components of the response of that structure, the dynamic oscillation and the static deflection. So you combine the two of those together and you get this guy here. Okay, so we can just tidy up the rest of this plot now by this top plot by doing the usual bits and pieces to it. So we're adding the axis labels, title, we're adding the legend, setting the X limit. So you'll notice it's just slightly different syntax because we are indexing to the first axis here. So let's just tidy that up. Excellent. And now just for completeness, I'm just going to repeat this plot just below it here for comparison. And so I can literally, let me see, I can copy this down, change it now because we're indexing into the next set of axes, and we'll change that to static, and we'll call this static. Okay, now let me see, I don't want static, do I? I want just the response. Okay, excellent. So let's just tidy that bottom plot up. Okay, and the last thing, let me see. No, that'll do us for now. Okay, so hopefully you can see how simple this is. Once we've understood the Duhamel integral, we've packaged it up into a little function. We know a little bit about modal analysis and how to simulate the first mode of this particular bridge, and it's thereafter. It's really, really easy to simulate the response of a pedestrian moving across the bridge. Really, really easy. And in fact, once we've done it for one pedestrian, it's going to be really easy to scale that up for a crowd of pedestrians. So one other thing that I want to do that's going to help us along the way is I'd like to be able to, if we just focus on this plot down here for a second, I'd like to be able to identify all of the peaks here. So all of these peaks, so that I could plot an envelope of response. Right now, it's a fairly trivial thing. You don't really need it when you're looking at a simple oscillating pattern like this. But when we get into, you'll see it now when we start to simulate 100 or 200 people walking across this bridge, the vibration response of the bridge is going to get very messy looking, and it's going to be quite handy for us to be able to just pick out from that kind of messy oscillation the displacement envelope. So I'm going to write a little function now that allows us to feed in this displacement, so the displacement here and the time vector, and it's going to search through and it's going to identify the time and the magnitude of each of these oscillation peaks so that we can plot an envelope over the displacement. All we have to do is for every point, so for every displacement, we're going to look at the current value of displacement and then the next value, the one immediately after it, and we're going to calculate a slope for the displacement. Now, if that slope changes sign, right, so if it changes from, let's say, a positive slope to a negative slope, well, then we'll have identified a peak. Okay, and that's basically all we're going to do. We're going to save those peaks and the times that they occur. So again, we'll define a function. We'll call it peaks, and we'll say that it takes a displacement and a time. The first thing I'm going to do is it's going to return a set of peaks and a set of corresponding times. And so I'm going to initialize a container to hold that data. So I'll say peaks is equal to, from NumPy, I'll define an empty array, and I'll say this empty array has one row and currently 0 columns, but we're going to add to that. We're going to append values into it. And we'll say that obviously we need a container to hold the times as well, and that's going to be the exact same thing. So let's give ourselves a bit more space here. So the first thing I have to do is I have to work out for every point along my displacement oscillation there, that blue line, I need to work out what's the slope. Okay, so calculate the slopes for each data point. So again, I'll define a container here. I'll say, I know exactly how many slopes I'm dealing with here, so I won't bother defining an empty array. Instead, I'll define an array of zeros. That's the correct length. So it's going to be zeros, and it's going to have how many elements? It's going to have a number of elements that is the same as the length of the displacement vector. because we need a slope for every one of our displacements, except for the very, very last displacement value, because obviously there's no next displacement value to allow us to calculate a slope. But that value will automatically be 0 because we're defining an array of zeros here. All right, so now that I've defined a container that's gonna hold all these slopes, I can cycle through each of my displacements. So we'll do this in the usual way, setting up a for loop. So we'll want an iterator I. We'll say u is the value of the displacement every time we go through the loop. So we'll say enumerate. We need to use enumerate if we want the counter, and disp. Okay. All right. Now the first thing I need to do, as I said, I can't calculate a slope for the very, very last displacement value because there's no next displacement value. Then I need 2 values to calculate a slope. So I only want to do this slope calculation if I is less than the length of the displacement vector minus 1. Okay, so if I is less than, that means it's going to stop trying to calculate slopes on the second last displacement value. All right, so once we've got that caveat in place, I can go ahead and calculate slope. So I'll say slopes I, so we're calculating the value that's going to slot into position I, and that's going to equal, now all I really have to do here is check the difference between the next value of displacement and the current value of displacement. So I'll say disp, let me see, so I want I plus 1, so that's the next value of displacement, minus the current value of displacement. Now if it was a true slope I was calculating, I would take that height difference essentially and I would divide it by the time step between those values, but I don't really need to divide it by the time step because all I'm looking for is a sign change in the slope, not the absolute value of the slope. So now that I have that done, I've got all that loop, that for loop will cycle through and get all of my slopes for me. Now I can cycle through all of those calculated slopes and look for sign changes to identify a peak. So we'll set up another for loop. So for I, and this time we'll say the slope is going to be denoted with an S in enumerate slopes. Okay. And again, we're checking the current slope and comparing it with the next slope. And so we don't want to do that on the very last value of slope because there will be no next one. So we'll say only do the following if I is less than the length of slopes minus 1. So now here comes the test, right? So if the next slope, so not the one I'm currently on, but if the I plus 1 slope, if that happens to be negative and the current slope is positive, well, that means between the current one and the next one, there was going to be a peak in my oscillation. And so I'm going to save out the current peak and the time, right? So let me just write the condition first. So I'll say if slopes I plus 1, so if the next one happens to be negative and the current one, so that's going to be slopes I, happens to be positive. Okay, so if we satisfy that condition, well, let's save into peaks, right? So we'll just say peaks. Remember, that was just an array, an empty array, so we can append into it, just keep adding values onto the end of it. So we'll say np append, and what are we appending onto? We're appending onto peaks, and what are we appending? The current value of displacement. Okay, disp I, and we'd like to also save the time. The current time, so that's going to be times is np.append. We're appending onto times and we're appending the current time. And then the last thing, which you can't forget to do, is return out of the bottom of this function the values that you just calculated. So we calculated a whole load of peaks and a whole load of corresponding times, and there we have it. Okay, so provided I have no typos in there, that should work. So let me just execute that cell to define the function, and now we can call the function, right? So this is the big test. So let's call it, and we're going to pass it in. Let's pass it in the response and the time vector, and let's assign the output of the function. Remember, it returns two sets of outputs, right? It returns peaks and times. So I'm going to assign those outputs here to variables outside of the scope of that function. So I'm going to give them the same names because they're outside the scope of the function, so I can. So peaks and times is equal to our function peaks that we pass in response and time to. Let's run that. Okay, excellent, no errors. All right, now let's just plot it and see if it worked. Okay, so usual, set up a figure and a set of axes. We're not doing subplots this time, a single plot will do. So we'll say axes.plot. We're going to plot time against, first of all, the negative of the response, and we'll just give that a label. Then we'll plot axes.plot. Now we need to plot not time, but times the individual vector, or the vector of individual times at which peaks occur in the oscillation. So that's going to be times versus peaks, and that can have a label. Well, first of all, let's define it as a red line, and it can have a label. All right, and let's bring in the usual bits and pieces to tidy it up. All right, let's run it and see. Okay, nearly. I forgot one thing. I forgot to make that a negative of the peaks. Okay, there you have it. So that's what we wanted to achieve. So is it essential? Is it needed in this particular case? No, not really, because it's pretty easy. You can look at this oscillation and you can identify visually the envelope yourself. But as I keep saying, when we start to simulate 200 or 300 people walking across this bridge at the same time, that oscillation is going to look very, very messy, and being able to pick out the peaks or the envelope of response is going to be quite handy. So the last thing that I want to do in this lecture is I'd like, now that we have this kind of neat way of visualizing the envelope of response, I'd like to use it, right? So what I'm going to do is I'm going to run like a mock sensitivity study here, right? So I'm going to say, well, what does the vibration response to the bridge look like if I start changing some of the bridge parameters? And this is the type of thing that you could use this kind of modeling for, this kind of exploratory modeling, testing out how different bridge parameters or different crowd parameters influence the dynamic response to your bridge. So we're kind of doing a sort of a simple toy case of it here, but you're going to get the idea, right? So what I want to do is, in our case, I'm going to consider the influence of bridge mass per unit length. Right now, so you can imagine a scenario here where you're sort of at the early stages of designing a bridge. You know, it's a footbridge, and you might sort of be thinking around what kind of construction or materials you're going to use, and that's going to have an implication on the weight of the deck, the weight of the overall bridge per meter run. And you might want, it's going to be pedestrians walking across it, so you might want to get a feel for what's the response going to be for different weights of bridge deck. Let's say very, very simplified case, but you get the idea. Now, intuitively, we can say, well, okay, the heavier the bridge deck gets, the lower the natural frequency. And so, if your natural frequency is starting off quite high or above the average pacing frequency, the heavier your bridge gets, the lower that natural frequency is going to get. And it's going to bring it down closer and closer to your average pacing frequency, which is generally bad news. And that's what we're going to see here. So what I'm going to do is, first of all, let me define the stiffness of our bridge, because we're going to need that. So we'll define the stiffness based on the original set of bridge parameters. So we'll just say the stiffness is going to be m times the natural frequency squared. Okay. Now what I want to do is define a range of masses per meter run for our bridge deck, right? So we'll say we're testing out 3 different cases. A bridge deck mass of 1750 kgs per meter, 2000 and 2250. Okay. And now what we want to do is run our simulation, simulate the response for a person walking across the bridge with these different masses. And so it's a relatively easy thing to do. So I'm going to set my figure up, and then I'm going to go into a loop that loops through each case and adds a new line to the figure on every loop iteration. So we've kind of seen this pattern before. So I'll say for m in masses, so looping through each of our masses, let's define the modal mass as being equal to, again, a half the total mass. That then sets up our natural frequency for this case, which is going to be the square root of k over m. That's why we worked out the stiffness at the start. And then we want the damped natural frequency, which is going to be the same as we had before, the natural frequency times the square root of 1 minus xi squared. All right, now we can go and calculate the response in this case, and that's going to be equal to Duhamel, and we're going to pass in time. Now the force, the modal force doesn't change, so we're relying on the global definition, or the previous definition I should say, of the global force, or the modal force. And now that we've got the response, we can call peaks. That was with a capital P, peaks, and we're going to pass in response and time, and we're going to assign the output of that to peaks and time. All right, and now that we have that, we can plot it onto our graph. So axes dot plot, and let me see, we're plotting times against times against the negative, don't forget, of the peaks. So this is where this comes in handy, right? I don't want to plot time versus response because I'm going to end up with, you know, a mess of 3 different oscillations that are fairly similar, lying on top of each other. It's going to be very hard to make out what's going on. But if I plot the peaks, I'm just going to get 3 clean lines that are sort of just offset from each other. So it gives me a much clearer picture of what's happening. So we'll say, let me see, time versus negative of peaks. We'll give it a label. And again, we'll use an F string because we're going to want a variable within our string. So we'll say label is equal to F. So F and then the string. So we'll say response envelope M equal to, and this is where we can put a variable in, and we'll just put in the current value of M, which again is updating every time we come through the loop. All right, and then we'll add our housekeeping on the outside of the loop. Again, that only needs to be added. So reversing our indent, stepping out of the for loop, and then putting in our housekeeping at the very end after we've added our 3 lines onto the graph. Right, let's see what that gives us. Oh, that's disappointing. What have we done wrong here? X and Y must have the same first dimension, but have shapes 88 and 87. So what have we got? We have an issue here. So times and peaks. Let me see. I can see what the issue is. I think this needs to be, I put in time, that should be times. Okay. And now because I've redefined erroneously, I redefined time here. I'm going to have to make sure I go back up and correctly define my time vector for this notebook, which was, where was it? Okay, so up here. So let's just run this cell at the very top of the notebook again, just to make sure we're correctly defining the time vector. Okay, now we can go back down. Okay, excellent. All right, so here we have it. So we can see pretty much exactly what we expected to see. So this is the response envelope for those 3 different simulations. And sure enough, you can see as the mass of the bridge deck gets larger, that means the frequency, the modal frequency of our first mode of vibration is going to get smaller, which brings it closer because it started off at 2.5 hertz. So the orange line here corresponds with the red line we saw previously, and we can see if we reduce the mass of the deck, well then the oscillation amplitude essentially reduces because we are increasing our natural frequency, which draws it further away from the pacing frequency in question. But if we increase the mass of the deck, we're reducing the frequency of the bridge of the mode of vibration, and so it brings it closer to that pacing frequency, and so you're going to get a larger response out of your bridge deck. So this was a very, very simple example of a sensitivity study, but once you wrap your head around this kind of simulation and you start building these simulation tools, this is the power of it really. You can, do these kinds of sensitivity studies, much more elaborate versions of these studies, and get a real sense of how your structure is likely to behave as you change different parameters. Okay, so we'll leave that there. In the next video, we're going to come back and we're going to expand on this and start thinking about simulating many pedestrians walking simultaneously across the structure. That's going to be quite interesting. So we'll pick that up in the next video.